Welcome to lecture 17. In this lecture, we will cover demographic models, and this is the first part. So, the different concepts that would be covered in this lecture are demographic models, demographic projection techniques, parametric and semi-parametric models, demographic projection techniques, mathematical methods. So, we will go into detail of mathematical methods in these concepts, and the other methods would be covered in part 2 of this lecture. So, demographic models basically refer to models where we actually try to predict the different values of demographic indicators in a future time period. For that we need to build models, and these models not only help planners or researchers to detect and correct wrong data, impute missing data and predict from existing or partial data using mathematical or statistical formulas. So, these models, what we can do is when we have a model, we can predict, and when we can predict for future years, and if we do that, then even if we have some wrong data or if there is a missing data, we can fill up those gaps by using these models. And we can predict from existing or partial data also. That means if we have only a partial data of a population of some population subgroups, then we can also using these models we can predict for the entire population. So, in these models several indicators are studied such as mortality rate, fertility rate, population growth rate, total population and so on. So, that means when we are talking about demographic models, it not only covers the total population, it covers all the different components as well, like the mortality rate of the population, the fertility rate, how it increases over time and so on. Demographic models not only focus on time to determine trends, but can also predict trends across societies, regions or subpopulations. So, that means demographic models can also predict that over a time period there is certain change in fertility of a particular population age group or a particular, or for the female population for a particular area, but it may also have a certain trend over across several geographic areas. So, that also could be predicted. Urban and regional planners use population forecasting for effective policy design and for determining planning interventions. So, predicting population is the most important task of demographic modeling, and population projections are the starting point also for land use and transportation planning, which is the focus of this course, and also for economic and infrastructure development. So, if we can project the population, and not only the population, the different demographic indicators as well as the population components like as per age and sex groups, if we can project this data, then only we can start planning for a future time period. That means when we are doing a land use transportation plan for an urban area, we need to first ascertain what is going to be the future population, and then again this future population has to be determined not only for the total population, but also for each individual population subgroup, and then the population subgroup based on its, as discussed in the previous lecture, it could be a 2-dimensional one, 3-dimensional one or so on. That means we need to have subcategories, like for example a population group of a certain income category belonging to a particular gender and a particular age group can be a small population subgroup. So, population growth is also presented in form of a range with high and a low estimate. That means whenever we are, because since we are projecting the population and there are so many unknowns, so it is better to have a range of estimate with a high and a low value instead of having a single value. So, population forecast is not necessarily the most probable future. That means when we are talking about population forecast, we are in most cases we are assuming the current fertility and the mortality rates of the population along with fixed number of immigrants who are coming into the particular urban area, which is exogenously determined or based on certain estimates or based on previous historical data and so on, and using this we can predict population for a future time period. But as you can understand that because we are using older or existing current fertility rates and mortality rates, there maybe we are not forecasting it perfectly, but still it's a population forecast which could be used for future determination of policies, and it could be used for determining the future policies and the future activities of that particular area, but it may not be the most probable future. So, we are not determining the probability of a likely population figure for a particular time period. So, population growth can also be predicted by estimating actual probability of future mortality, fertility and migration rate to test the effects of various policies. So, sometimes we can also do detailed studies where we can determine what should be the future mortality rates, future fertility rates based on other indicators or other relationships that these particular indicators have with like for example age or with the income levels and so on, and then we can predict future values for these particular indicators, and from that we can also estimate the final population. So, that would be a more better estimate, but it is again very difficult. Many people also formulate laws of population growth to predict future changes. That means they find those relationships that okay, mortality is related with age. That means the more there is the age increases, there is higher chance of mortality. So, they may form a certain law or a certain rule, and usually it matches to some extent with the population of certain country, but we may find that when we try to fit that same equation in another country, it may not fit, or we may want to fit that data for all age groups, that particular relationship for all age groups, it may also not fit. So, in many cases actual events does not match this theoretical expectations. So, once we know that these are the different kind of demographic models that we have to form, we can understand, we have to develop these projection techniques for different demographic indicators. So, URDPFI has listed two simple techniques, two ways of projecting particularly population. So, these are simple techniques where we just project through extrapolation, and then there are analytical techniques where projection values is the dependent variable and is based on some independent variables, that is based on certain relationship. And in other literature we have found that different projection techniques, particularly population projection techniques, are listed as mathematical methods, economic methods and component based projection methods. So, these are the three primary ways we can project population. But before we go into projecting population, there are so many other parameters like mortality, fertility, which needs to be also projected, and for that we can develop parametric models or semi-parametric models. And as we know that demographic indicators vary across different age groups. So, this could be actually determined using these parametric models, like how this particular demographic indicator like mortality, fertility varies between the different age groups. And here we can say that we can form a relationship using certain parameters that okay, this particular fertility or mortality is related with few parameters like age, gender, or it could be based on certain income group and so on. So, these are the parameters. We would like to keep this number of parameters as less as possible, and there must be a function which relates this with the actual demographic indicator, and which is called a shape component. And then which this captures the age effect. That means higher the age, this function actually predicts it as per that. This function shows how the different age groups are related with this demographic indicator. And then there is a modification component in this equation, which is basically that which reflects the group's membership. What it means is there are several age groups. Because this population is in this particular age group, there has to be certain changes in the equation or certain considerations in the equation. So, the form of the equation has got the functional form shows or relates to the shape component, how this growth happens, and the parameter values is related with the modification component. Now, this could be done with a curve fitting exercise with existing data. So, we have existing data. We try to fit a particular curve. It may be an exponential curve, or it may be a linear relationship, or any kind of pattern we can try to fit in that, and whichever shows the best relationship, we can adopt that particular function. So, Gompers in 1825, he said that mortality rates in humans increase exponentially with age. So, this is a particular law that is being framed, and this function is we can call it in form when we make a parametric model out of this, we can say mortality or hazard is a log linear function of age. So, as you can see over here. So, we have got mu x, which is mortality at age x, we are taking the log value, is equal to a plus bx, where x a is the parameter for level of mortality at young age, and b is the parameter for rate of increase in mortality with age. So, that is how our particular relationship is being defined, and a and b are the parameter values which is modified as per the age group. That means, for young people their A mortality is less. So, that is why A value could be a fixed value, and then B value will change with that particular age group. Similarly, for determining the age pattern of first marriage, Cole made or suggested a double exponential curve function, and as given over here, two exponentials are taken. So, here Rx denotes the hazard rate or risk of first marriage at age x. So, that means, at what is the likely chance of a girl marrying at a particular age, or the risk of a girl marrying at a particular age. So, this is again a parametric function trying to find that at what age a girl is likely to marry, because that will lead to maybe childbirth and so on. So, these are the different this is how we can estimate the different indicators and how it is related with age groups, and even as we can say that when a population transitions from one age group, or a group of persons transitions from age group to another, how the fertility rates or how the nuptial rates will change. So, that could be determined using this equation. But both of these equations, as we can see, that they may fit to a particular population, they may not to fit to a particular population, or for it may not fit with different age groups. So, to ensure better fit, we can restrict the use of these equations to certain limited number of ages, or we can add some other parameters in the equation to make it more flexible. So, these are the problems with this kind of equation, and these models also lack behavioral and theoretical interpretations for different parameters, because we are finding the best curve fit, and then we are saying that this is how the population fertility rate will change, or this likelihood of a person marrying at a certain age will change, but actually there are no theoretical interpretations for that. And parameter models are also difficult when we compare two populations, because the parameter values A and B values will change, as we are seeing in the previous equation, and that will make it difficult to compare between the two populations. So, in semi-parametric models, this is taken care of to a certain extent, where semi-parametric models are mostly similar to parametric models, but this allows age dependency to be unconstrained. So, that means that age pattern is empirically estimated. That means changes in the values of those parameters is estimated from some empirical data. So, usually we like for example Brass in 1968 he created some relational life tables, where for example we have for different age groups he has given certain mortality values. For age group 15 to 25 there is a certain value, for age group 25 to 35 there is a certain value, and 35 to 45 the rate probably increases, but there he has given some fixed value. So, mortality rate of maybe 2, maybe then 3, maybe 4, it may keep on increasing. But next what we do is, when we use the equation of course, so mortality schedule is modified by two parameters through a logit equation as given by Brass. So, here we can see the equation where we have two parameters alpha and beta. These are the parameters characterizing this particular population group or subgroup, like whichever age group they are in, and Pxj is the probability of survival to age x in population group J, and P star j x is the probability of survival of age x in a selected standard table. So, this is where that means this rate is being considered. Now, what it means is, if we survey a particular population, or we cannot survey the entire population, maybe we have got the mortality values of two age groups like maybe 15 to 25 we can get from survey values. We find it is around 3, or we can also have around 45 to 60 we have another value which is of a certain maybe around 5. Now, we can say that we will compare this with this value and also this with the value from the table, that standard table that is already there, and then we will adjust this alpha and beta values by based on this empirical data, and then we can compute it for all the other age groups which are missing from the data. So, surveys provide mortality data of some age group, and we can fill the rest by comparing this data with a suitable standard life table to determine alpha and beta values, which is already given. So, we can compare that, and we can based on the relationship that we can generate, we can fill up the values for the age groups which are not provided in the data set. So, this is a semi-parametric model. So, that is more or less adjustable compared to the previous models. Now, coming to population projection, as we discussed, there are different methods. So, in this lecture we will discuss only the mathematical methods, and the other two methods, the economic methods and the component methods, this will be taken up in the next lecture. So, in mathematical methods, here we predict population for a future time period using population growth rate from a past period or from another population showing similar characteristics. That means, we can either consider the growth rate of in previous time periods, and we can say the same growth rate is going to continue, or from population of similar characteristics in a different urban area, and we can say that, well, that area is almost similar and they are having this kind of growth rate, so we can adopt that as well. So, either predicting net rate of population growth, so we can predict either net rate of population growth could be predicted, or birth rates, death rates and rates of immigration and emigration we can also determine to predict the growth of each future period. So, we can individually predict this and then estimate the future growth for a future population growth for a particular period, or we can directly predict the future population growth. So, these are called mathematical models, since equations use rates as functions of time instead of specific factors or attributes which may influence the growth rate in a time period. So, unlike the parametric models, this actually considers only the previous population growth rates, which is a function of time, and it does not consider relationship with other components. Calculations are also for the total population, and we do not consider different population age groups. So, we do not say that for different population age group the growth rate is different. Subsequently, projected values of total, once the total projection is determined or the total population is determined after projection, then we divide it as per sex, age or other characteristics to get the values for each population component. Growth rate may not be constant and may follow a curve. So, instead of saying the same growth rate would be adopted, we can say the growth rate can also follow a particular relationship or a particular curve, and usually the logistic growth rate represents a trend of growth or a growth curve which is very popular, and this actually this particular logistic curve actually is something like that, where initially the growth rate is low, then it picks up and then again it stabilizes. So, and stabilizes and almost becomes 0, there is no further growth rate. So, it is almost 0. So, this follows the universal biological law of growth. So, many things in nature actually show this kind of growth pattern, and that is why logistic growth curve in cases in many cities or many urban areas where there is normal growth, there is no special event, we can follow a logistic growth curve and it gives very accurate results. So, this method is applied if population growth is regular and there is no major societal and economic changes, and age structure, that is for logistical curve, and age structure should also be consistent, That means the age structure also doesn't go through very radical changes. In case there are a lot of changes in the above population characteristics, future arithmetic or geometric rate of growth can be modified by a certain ratio from present rates. That means if we feel that there is a lot of change in the population characteristics in the coming years, we can, instead of using direct future arithmetic or geometric rates that will be shown in the coming slides, explained in the coming slides. So instead of logistic curve, we can use a linear increase rate or a geometric increase rate like this, and we can say that in future years the geometric rate that we are estimating for previous years, we can also increase it by a certain ratio. But the problem is the logistic curve method, we cannot modify the particular rate. So we have, in mathematical methods, we have got several sub methods: arithmetic increase method, geometric increase method, incremental increase method, logistic curve method, and graphical methods are not arithmetic methods, but it almost could be because it is done manually, it's using graph paper. We can say that it is similar to almost this kind of methods where we just extend the previous growth. And there is also we can say that we can also take the population from other urban areas, and following that we can also model that growth in a particular urban area. So that means this kind of models actually assume that this current urban area is following the similar economic and social or growth pattern as the urban area A is following same as B. So that's why we are taking the growth rates of B and putting it for A. If we don't have data for A, whereas we have got data for B. But similarly, we can say that if we have one urban area and we have a larger urban area, we can adopt the growth. If we have data for the larger area, we can adopt the rate for this particular overall area for the smaller area as well. So this could be called a mathematical method, but it could be also called an economical method, because we assume that the same economic growth pattern of the larger area is being adopted for the smaller area. So this will be covered in the next lecture. So in arithmetic increase method, which is pretty straightforward, the rate of change of population with time is constant. So dp by dt is the rate of population change, and m is the population growth rate, pt is the population at time t, P0 is the initial population, and T is time in decades, or it could be even every year, doesn't matter. So we see that Pt is equal to P0 plus Mt. So P0 is the initial population, and Mt is just multiplying the rate, the population growth rate with the time period. So in example, you can see over here, this is pretty again straightforward. We have got data for 1991, 2001 and 2011. This is the population data for Mendipur district, and what we can see is we can estimate, using this data we can estimate the population for year 2021 or 2031 using this method, where we see here that we are first estimating the increase in the population from 1991 to 2001. So the first decade, and we see there is a huge rise over here from 8,20,000, it becomes 8,38,000, 8,38 lakhs or 83 lakhs, sorry, and then it again increases further over here, and then we can also compute this value. And now that we have got two increases, we take average of those two increases as shown over here, and this is the increase per year, average increase per year. And then if we want to find the population for year 2021, which is roughly 3 decades, we divide by 10, we get 3 decades, and we just multiply the base year data, that is 1991 data, with 3 times the increased data, and we get a value of around 161 lakhs over here, or 1 crore 61 lakhs. Similarly, for 2031, we get around 2 crore 11 lakhs 97,669. So this is a very simple way of extending or projecting the population, and but some problems may occur. As you can see, there is huge increase during this period. from 1991 to 2001, but then the increase has slowed. But when we are estimating the population for a future year, we are not considering this change in rate, change in the growth rate. Then coming to geometric increase method, in geometric increase method it is assumed that percentage increase in population is constant with time. So here the formula is Pt equal to P0 into 1 plus m to the power t, where t is the time in decades again, P0 is the initial population, Pt is population at time t, and m is the average geometric rate of change. So we are taking the geometric rate of change and the average value for that. So as in example we can see the same, we are using the same population figures. So here we can see this is the increase value as estimated earlier. We see there is an increase of around 10 times. That means the population here has increased by 10 times. Then in 2011, we can see that the population has increased by only like 0.19 times. So which is a much less. So average increase is estimated through geometric mean, which is both of them multiplied, and then we take a root of them. If it was 3 times, then we have taken we would have taken to the power, this would have been 1/3, 0.33, and then using this method we can estimate that Pt equal to P0 plus 1 plus m to the power t. So for 2021 we take the base year value plus 1 plus the rate to the power 3, and then for this one to the power 4, and we get a population of 115 lakhs and 277 lakhs during these 2 time periods. So if I had got 2021 data, then we would have 3 values, and then this would have been the geometric mean of these 3 values. So in incremental increase method, this method is an improvement upon the previous 2 methods, but again there are some issues with this method as well. So here we divide the increase of population into 2 parts. One is the average, the first is the average of the increase in the population is estimated by arithmetic method. So that means we determine the straightforward increase in the population over here, and we take the average, this is a total increase, and we take the average increase per year, which is 15,800, and then we estimate the net incremental increase is also estimated. So here we increase that, okay, how much is this change happening? That means every year how much amount of change is happening between the 2 years. So here we can see that there is change of 2000 in the amount of increase that has happened, and then for the next year there is 5000, then there is a negative change. Then we take average of this and we get a average increase of 2067. Now what we do is we estimate the total population at time t by taking the initial population, and then we have got 2 components. The first is t into m, where we multiply the time in decades into the rate of increase for each decade. This is similar to arithmetic. And then we add another component where we multiply k, which is the rate of change in increase for each decade, which is this one, into t plus 1 divided by 2. So this is based on the number of time periods we are estimating for. So if there are 3 time periods, so 3 into 4 divided by 2, so that is into 6. So here we can see if we using this method, if I estimate the population for year 2021 and year 2031, we have the base year population 52,000 plus 5 into 15,800, which is the arithmetic part, and then this is the incremental increase part that we are estimating, and we get a population figure like this, and same we get another population figure like this. So if I draw this increases, you draw these projections, how it looks in a graph, we can see that the linear projection is pretty straightforward. That means it increases in the same rate. So this is arithmetic projection. In geometric projection, the rate of increase is low during the first years and then suddenly it picks up. So, this could be applied in cases when there is transformation in the society, like lot of industrialization is happening. So, there is over here, and so there is lot of change. So, there is lot of change, and suddenly the population starts growing. So, here geometric projection may be useful, but in most cases it is very difficult to use this kind of projection because it will it overestimates. And then we have the incremental increase method, where we have seen it's a little bit in between both arithmetic progression and geometric progression, but the progress is but the rate of increase is more appropriate. And then if we compare these three, we can see these are the two variants. So, this is linear, this is the arithmetic projection, this is the incremental increase, and this is the geometric increase. So, finally, we come to the logistic curve method, and this is used when the city is growing normally and not experiencing any extraordinary events. So, when the population of the area is plotted against time, and the resulting curve will be S-shaped as discussed earlier, that means it would show something like this. And the mathematical solution to this logistic curve, which was given by Worrells, is given below. So, this is the mathematical solution for this, where k is a constant value over here, and Ps is the population at saturation. So, this is saturation value of population. So, Ps, P is the population at time t from origin j. We are trying to estimate the population at a certain time period, and P0 is the population of an area at point j, that is the starting point population, and T is the number of years. So, we can say that based on this particular equation, where we are taking where we are estimating taking the saturation value into k and into time period t on this side, and we have the log values of both, where we are taking both Ps minus p divided by p and minus log e, and to the again with Ps minus p0 by divided by p0, and we finally come to the point where p could be estimated as the saturation value divided by 1 plus m into log e to the power minus 1 nt, where m is Ps minus p0 by p0, which is population at saturation minus population of that initial population that we are talking about, and n equal to minus k into p to the power Ps. So, Ps is the saturation value of population. So, this particular equation, this was further worked on, and MacLean suggested three observations suggested that based on three observations we can predict the population at a certain time period using the logistic curve method. That is, if P0, P1 and P2 at time T0, T1 and T2 are available from historical records, and we take that T0 is the 0th year, the first time period, and T1 and T2 is related, so that T2 is equal to 2 times T1. So, we have equal gaps between the two time period. Then mathematical expression for calculating Ps, m and n can be written as Ps equal to 2 P0 into P1 into P2 minus P1 square within brackets P0 plus P2 n bracket and divided by P0 into P2 minus P1 whole square. And m remains same, and Ps minus P0 by P0, and n equal to minus 2.3 by T1 into log to the base 10 P0, and as you can see over here in the equation. So, using this formula for the year for this particular example, we can see that we have population in 3 time periods, and P0 is 78,000, that is time period 0. Then P1 is 97,000, which is time period 10, and P2 is for 1,15,000, which is for time period T2, which is 20. So, this is the first decade and the second decade, and we can estimate Ps using this particular formula, which comes to around 17622, and m value is, this is the saturation population beyond which the population will not grow further, and we can estimate this is the m value, and n value could be estimated over here, and putting it in previous equations from the last page over here, this equation, we can find that P for the year 2021 could be estimated as 17622, which is the PS value, and divided by this particular based on that previous equation, and we get a value of 1,18,270. So, this is the projected population for year 2021. So, this is how we can get this using logistic curve method. So, finally, we come to graphical method, and as you can understand that all the other methods that we discussed till now, they are to some extent making assumptions such as the growth rate will remain same. Then in the next one, we are following a geometric growth rate, that is there is increasingly the population growth will accelerate, and then we have the incremental method and the logistic curve method. We are assuming that there is going to be a saturation value. So, in addition, we can also follow a graphical method, where based on we can first plot the existing data that we have got for different population data for different time periods. In here what we can do is population is plotted in the y-axis, and year or the time is plotted in x-axis, and it could be plotted in a suitable scale to so this will actually help us to understand the past trend in a visual way. So, we can see it is not exactly straight, it is a curve to some extent. So, this growth curve can be extended smoothly to estimate the future population by comparing the curve with the curve of other cities with similar growth pattern. So, that means we can understand that population with this kind of cities with this kind of curve, how they have grown over time, and we can also adopt the kind of curve those cities have taken, and we can extend this curve. And usually this could be done for short term population projection and not for very long term projection, because there is a lot of without any particular methodology, we can end up with a lot of assumptions on the on the part of the person who is actually doing this extension, who is doing the extension. And then this could be done for projection periods maximum of 10 years. And if it is the different demographic trends are stable, that means population is stable, then we can do a maximum for 10 years, where for volatile trends, that means the population is going through a lot of changes and all, then this kind of method could be adopted only for 5 years. So, these are the references you can follow. So, to conclude, demographic projections are undertaken for both population and other demographic indicators. The projection method adopted is as per the geographical area, demographic characteristics, their rate of change, and the projection time period. An incremental increase method and logistic curve method are the most popular mathematical methods for population projection. Thank you.